Hi Year 12. So this video we're looking at exercise 12b in the Cambridge textbook, and we're going to have a look at the integration of inverse trig functions. Now before we get into any of the questions, let's have a look at what the HSC formula sheet has on there for you. And this is what we've got on there to the right over here. So I don't know if you go and have a look at the sheet yourself on the integral page, towards the bottom, mid-bottom on page number 3, you're going to find these two formulas. And what you will notice, it's a little bit like when we're integrating with logs, is we're not integrating the log, we're integrating something that will become a log. And that's the same with our inverse sine, tan and cosine, which I'll show you in a moment. We're integrating something of this format, and if it is in that format, we're going to get an inverse sine plus c. The same with the tan. If something is in this format, when we integrate it, we're going to end up with an inverse tan. But we don't integrate inverse sine and we don't integrate inverse tan. We integrate things that look like their derivative, and that's what we end up with. So remembering back to last lesson, and I'll hop up to that. Okay, the stuff in our blue cloud here is our differentiation formulas for our inverse functions. So we had this as our function and the derivative was this. So remember, when we're differentiating, we're going this way. But if I integrate this, I'm going back the other way and getting my inverse. So that's basically what's happening. This is my function. I differentiate it to go this way. But if I integrate something that looks like that, I'm getting my original function. So that's what's happening. Now, while we're up here, let's just note that when we had y is sine inverse and y is cos inverse, have a look at their derivatives. The only difference between the two is that negative. So on the HSC formula sheet for the integral, they don't pop the cos formula in there. We can pop that in there ourselves, and I'll go and show you that now. Okay, so they are the two that are on our HSC formula sheet. So if we integrate something that looks like this, we get sine inverse of the function. But if I just scroll over here, we could also get minus cos inverse of that function as well. But we don't get that given to us. We need to know that, and we can work that out from the differentiation part of the sheet. So we can get sine and tan and cosine inverse. Just need to remember this one. Okay, let's go and have a look at some questions. Okay, so let's have a look at the first question. It says basically these use the same rules as those that are given to you. So here's our first question. We're going to integrate something of the form dx over the square root of 1 minus 4x squared. That dx can be moved up there. We would have normally put a 1 up the top there, and we haven't really seen it like this before, but that's another way of writing it. It doesn't have to be at the end over here. Now, I'm looking at that, and I'm looking at my 3 inverse rules for sine, cos, and tan, and I know it's not tan because there's a square root there, so we can use sine. We could use cos. I've just popped the rule over here, so this is the rule. So we want to see if we can get this question into this format. So what the rule says is we've got to have a squared, well, we've got 1, so that looks okay, minus the function all squared. So we need to rewrite this. So what we have on the bottom line is something that is a function whose answer squared is 4x squared. So the x squared part's there, so if we just take the square root of the 4 and have it as 2, we can write that as 2x all squared. So if we were to open those brackets up, we'd end up with 4x squared. And that takes on that format there. Now, if that function there, which is our 2x, is on the bottom, it's saying that the derivative is on the top. So the derivative of f of x is going to be 2. So this is the format that we have up here. But our question, we've just made 2 times bigger. So I need to have basically a 1 up the top, so I need to halve it. So the half and the 2 will now give us that 1. So that's the format that we're working in. So the half is going to stay there because I've halved my integral, but my integral here matches with this one here. So we're just going to write sine inverse of the function, which we said was 2x, over a. A is 1, so I don't need to do that, plus c. So it may bring back some memories back to your year 11 integration, and that's great because that's how we're going to do these. Now, if you remember the rule that we looked at right at the start, we said that things that were equal to inverse sine were also, so when I say things, I mean integrals that were equal to inverse sine are also going to be equal to negative cos inverse. So what we theoretically then could do, I don't know, I always seem to go to sine first, but that would also be equal to minus a half cos inverse 2x plus c. Okay, let's look at the next one. Evaluating between half and 0 of dy of 1 minus y squared. The dy would be just to do with the y-axis. In this case, it doesn't matter. We're just going to be doing it the same way. And we're going to have a look at our rules. Well, it's going to be a sine or a cos inverse because we've got the square root. Just noting that the tan inverse integrals don't have that square root. So that's what's giving us away that information first. So let's see if we can get it into the format that looks like our rule. So we've got a 1 dy at the top. Okay, I'll pop the 1 there so that you are comfortable with that. And down here we've got y squared. So the top line is the derivative of that y, which is 1. So we've got that, haven't we? So it looks like we've got everything in the right format already. So we actually don't even need to do anything else. We can write it straight into its integrals. Answer, a half and 0 sine inverse of the function is y. So note the rule's got the function squared, and we pop the function up there. So the function squared is y squared, so the function is y. Popping our values in, sine inverse of a half, oops, minus sine inverse of 0. Pop that in your calculator, or you probably know what it is by now. So sine inverse of a half, if we're thinking degrees, it's 30 degrees, but I'm going to pop it in radians, which is pi over 6, minus 0, which is pi over 6. Okay, so our next example. Find the area bounded by the curve y is equal to 25 minus x squared, or to the power of minus a half. It's a little bit hard to see, but that is a minus up there. The x-axis, so we know that it's not the y-axis, and the lines x equals 0 and x equals 3, and it's corrected to significant figures. So there's a lot going on in there. Area lets us know we're integrating. It's between this curve, which is a negative, so all that's on the bottom line. The x-axis, so we're going to have upper and lower limits that are x values, and these are our upper and lower limits. So let's write that straight in. We're going to integrate between 3 and 0. We're going to have it in respect to x, that's our x-axis, and we're going to be over the square root of 25 minus x squared. Again, you're looking at that, and that is of the form sine or cosine. I'm going to use sine. Okay. So when it's of the form sine, we're going to write that as the square root of that number out the front, which gives us 5. I'm going to square it. The rest of it looks like it's in the right form. So our function, remember, is x, because in the sine rule, we've got the function squared. And on the top line, we have the derivative of our function. So the derivative of x is 1. So that's what it's going to look like, and we're going to integrate between our upper and lower limits. So when I do that, we've got inverse sine of the f of x over a. So x over 5 between 3 and 0. Popping that in. Inverse sine of 3/5 minus inverse sine of 0. And we want it to two significant figures. So we're going to pop that in the calculator. Okay, so to get your answer there, I would be looking at radians in there. So you've got some options. You can pop your calculator in radians mode, in which case you'll get 0.63, etc. And to two significant figures, it's 0.64. Or if you don't like that, I know a lot of you don't, you can stay out of radians in your degree mode and work out that this is your value. But in order to get it to significant figures, and you're not used to doing this, you're going to be timesing it by pi over 180, which gets us into your radians. You're going to use the pi as a pi. Okay, so you're going to get 3.14, etc. over 180, and you'll also get the 0.64. That's your answers.